Okay, we're rolling. All right, so this is basically the same thing we did yesterday, just using Leibniz notation. So just like with regular chain rule, you have to be actually trying to find the derivative of something that exists over the domain that you're trying to differentiate it on. So if the derivative of y with respect to x, or the slope of y or the slope of the line y equals some function of x exists, then the slope of that line, or the rate of change of that line, is equal to dy by du times du by dx, where y is the function of u, and u is some function of x. So, in other words, I have some sort of x number, I perform function g to it, and then I get a u value. I perform function f on that, and then I get a y value. So think of it as the value of x changing, that changes u, which then changes y. So there's some function of x which has a slope that's u, there's some function of u that has a slope that's y, is what you're doing when you're differentiating. So the change in x affects the change in u, which affects the change in y. So this basically is the chain rule, just written in Leibniz notation. So for example, yesterday's lesson we would have looked at this thing and used our chain rule kind of formula. But now I'm going to think of this as y equals u to the 7. I'm actually substituting this part here as a new variable u. And so dy by du, right, the derivative of the function y with respect to u, is 7u to the 6. And I know that u is what I defined it as, x cubed minus x. So du by dx, that's a u, not a y, is equal to the derivative of this, which is 3x squared minus 1. So, according to the chain rule, the derivative of the original function y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x, which works out to be, so that'll be 7u to the 6 times 3x squared minus 1. And then to get a final answer without this extra variable of u in it, I just substitute back what I defined u to be. And there we have it. There's the derivative. That's the same thing we would have got if we'd have done it using kind of yesterday's method. This method does involve kind of thinking about it as a substitution of a second, or I guess I should say a third variable besides y and x. All right, we'll take a pause here for O Canada. Okay, we're back. Okay, so there's example 1. Let's move on to example 2. So using my new Leibniz notation, I am going to let u, oops, oh, that looks wrong. Let u equal the thing under the brackets, so 4x squared plus 3, and y then is equal to the square root of u. So that means that dy by du is 1/2 u to the negative 1/2, and du by dx, the derivative of u with respect to x, is, let's see, that's going to be 2 times 4 is 8, 8x, and remember the derivative of a constant is nothing. So the derivative of this entire thing, using the Leibniz method, I'll write the formula again, is dy by du times du by dx. So what's dy by du? It's 1/2, actually I won't substitute it in yet, u to the negative 1/2 times du dx, which is 8x. And what's nice about this method is before I plug back in what u is and get rid of this extra variable, I might notice some simplifications a little easier. Like I'll notice, oh, this 2 will cancel into that 8, making it a 4. And then this u to the -1/2 would probably look better down here, right? So now I substitute back in what u is and get a final answer of 4x over the square root of 4x squared plus 3. Okay, so there's example 2. All right, one more like this. So using Leibniz notation, I have to let, so y will actually equal u to the power of 7, and u I'm defining as the thing inside the bracket, 6x cubed plus 2x. Make that look nicer. So the derivative of y with respect to u is 7u to the 6. The derivative of u with respect to x is 18x squared plus 2. Check my mental math on that. Yeah, that's right. So in Leibniz notation, the derivative of function y with respect to x is the derivative of function u with respect to x times derivative of function, oh, sorry, I just wrote that backwards. I meant to say y and u first. Oh, now I'm racing too much. Sorry. Derivative of y with respect to u and derivative of u with respect to x. Sorry, that's what I meant. Okay, so let's put those two things down. So the derivative of y with respect to u is 7u to the 6, and derivative of u with respect to x is 18x squared plus 2. Okay, this guy doesn't really have anything I can do to simplify it or anything. So I'm just going to go now and substitute in my u value to get rid of this extra variable, and u is the function inside the brackets. Okay, so are there any advantages to this method over the other one? Because it actually kind of adds an extra step, right? Because you have to introduce another variable and then remove it again later. Well, most of the time probably not. The one time it might make your life a little simpler is when you have to actually find a value for the slope at a specific x point. So we don't have an example like that on the handout I gave you, so I've just made one up here. So you want to maybe just copy that one down. If you don't have enough room on the piece of paper that we're writing notes on, maybe use a piece of loose leaf. But we'll call this example 4 for today. I'll give you a sec to catch up to that. And your assignment's going to have a few like this. So we would like to find the derivative of y with respect to x if y is a function defined in terms of u, and then u is its own function defined in terms of x. And I could maybe also point out that, you know, this of course means that y would in fact equal 1 minus 3x squared to the power of 10 plus 1 minus 3x squared to the power of 5 plus 2. So that would be the function without having to resort to a third variable. So basically, remember what this question's asking. It's asking for this notation here. Let me get a highlighter going. There we go. This notation here is basically asking the question of that. It's asking, find the slope of this curve at the point where x is equal to 1. That's what this thing means. Okay, so we want the derivative of y with respect to x, which is the derivative of y with respect to u, times the derivative of u with respect to x. Which is, okay, let's see. What is the derivative of y with respect to u? So deriving this thing, it's going to be 10u to the 9 plus 5u to the 4, and of course the derivative of u is nothing. Or the derivative of 2, I mean, is nothing. Times, okay, the derivative of u with respect to x. Go to my u function. So the derivative of 1 is nothing, so that's going to be negative 6x. Okay, now, what's nice about the Leibniz notation, here's the one place where Leibniz notation maybe has an advantage, is I actually don't have to deal with this great big function. I can just go back, like I don't have to substitute this 1 minus 3x squared into the u, is what I'm saying. I can just go here and say, oh, I know x is equal to 1. So if x is equal to 1, then u is equal to, instead of 1 minus 3x squared, it's just 1 minus 3 times 1 squared, which is negative 2. And so I can take dy by dx, and instead of having to put in that binomial for the two u's in this expression, I can just put in the number, and it's a much less work and fewer steps in my calculation that way. So it's going to be, let me use a square brackets. It's going to be 10, and instead of u, I now know u is negative 2, so that's negative 2 to the power of 9, plus 5 times negative 2 to the power of 4, times negative 6, and x, remember, is just 1. And now I actually have to get a number for that. Okay, 2 to the power of 9 is 512 times 10. Oh, and it's a negative, right? A negative to an odd power. So that's negative 512 with a 0 on it. Plus 2 to the power of 4 is 16, but the negative goes away because it's an even power. And 5 16ths is 80, right? And that's just negative 6. And if you take 80 away from 120, you're going to get 40. So that's negative 5040 times negative 6. And I don't think I can do that in my head. I know it's positive. If you times 5,000 by 3, you get 15,000. So 15,120 doubled. 3240, am I right? 30 and yep. Yay. 30 and 240 is my answer. Now you're going to notice that one thing I didn't do for a question like this is what I usually do in these lessons is jump over to Desmos and kind of double check and see, yeah, does this line here at the point x equals this line here, at the point when x equals 1 actually have a slope that looks like this? Well, I mean, is there any point? A slope like this, a slope of a number that big would be, I mean, that would be such a steep slope, it would look like a vertical line to me. There'd be no way of kind of looking at it and going, oh yeah, that looks about right. So we've kind of entered the type of question here where going to a graphical solution wouldn't be any advantage. If I can't deal with the algebra and the arithmetic of it, I'm pretty much sunk. Okay? So there we go. That's the kind of question that you're going to see in the homework, is ones like this. And that's the same stuff we did yesterday, just with the slight change in the way I approach it. I use the Leibniz formula instead of the formula I gave you yesterday. If a question's on a test and it just says find the derivative and it doesn't say which way you're supposed to do it, I don't really care which way you do it. If you want to use the substitute in a u and Leibniz form, great, if that makes more sense to you. But if you like yesterday's formula better, that's fine too. Okay, that's it. That's today's lesson. Short and sweet.